A fluid flowing past the surface of a body exerts a force on it. Lift is the component of this force that is perpendicular to the oncoming flow direction. It contrasts with the drag force, which is the component of the surface force parallel to the flow direction. If the fluid is air, the force is called an aerodynamic force. In water, it is called a hydrodynamic force. Overview. Lift is most commonly associated with the wing of a fixed-wing aircraft, although lift is also generated by propellers, kites, helicopter rotors, rudders, sails and keels on sailboats, hydrofoils, wings on auto racing cars, wind turbines, and other streamlined objects. Lift is also exploited in the animal world, and even in the plant world, by the seeds of certain trees. While the common meaning of the word lift assumes that lift opposes weight, lift in the technical sense used in this article can be in any direction with respect to gravity, since it is defined with respect to the direction of flow rather than to the direction of gravity. When an aircraft is flying straight and level, most of the lift opposes gravity. However, when an aircraft is climbing, descending, or banking in a turn, the lift is tilted with respect to the vertical. Lift may also be entirely downwards in some aerobatic maneuvers, or on the wing on a racing car. In this last case, the term downforce is often used. Lift may also be largely horizontal, for instance on a sail on a sailboat. Aerodynamic lift is distinguished from other kinds of lift in fluids. Aerodynamic lift requires relative motion of the fluid, which distinguishes it from aerostatic lift or buoyancy lift as used by balloons, blimps, and dirigibles. Aerodynamic lift usually refers to situations in which the body is completely immersed in the fluid, and is thus distinguished from planing lift as used by motorboats, surfboards, and water skis, in which only a lower portion of the body is immersed in the lifting fluid flow. Simplified physical explanations of lift on an airfoil. An airfoil is a streamlined shape that is capable of generating significantly more lift than drag. A flat plate can generate lift, but not as much as a streamlined airfoil, and with somewhat higher drag. There are several ways to explain how an airfoil generates lift. Some are more complicated or more mathematically rigorous than others. Some have been shown to be incorrect. For example, there are explanations based directly on Newton's laws of motion and explanations based on Bernoulli's principle. Either can be used to explain lift, flow deflection and Newton's laws. An airfoil generates lift by exerting a downward force on the air as it flows past. According to Newton's third law, the air must exert an equal and opposite force on the airfoil, which is the lift. The airflow changes direction as it passes the airfoil and follows a path that is curved downward. According to Newton's second law, this change in flow direction requires a downward force applied to the air by the airfoil. Then, according to Newton's third law, the air must exert an upward force on the airfoil. The overall result is that a reaction force, the lift, is generated opposite to the directional change. In the case of an airplane wing, the wing exerts a downward force on the air and the air exerts an upward force on the wing. The downward turning of the flow is not produced solely by the lower surface of the airfoil, and the airflow above the foil accounts for much of the downward turning action. In some versions of this explanation, the tendency of the flow to follow the upper surface is referred to as the Coanda effect. This is a controversial usage of the term. Limitations of deflection. Turning this simple explanation, while correct in as far as it goes, is not sufficiently detailed to support the precise calculations required for engineering. Quantitative predictions require a mathematical theory as described below under mathematical theories of lift. Furthermore, this explanation does not explain pressure and velocity variations in the vicinity of the airfoil or how the airfoil can impart downward turning to a much deeper swath of the flow than it actually touches. A more comprehensive physical explanation below addresses these issues in a qualitative way. Increased flow speed and Bernoulli's principle. Bernoulli's principle states that within a steady airflow of constant energy, When the air flows through a region of lower pressure, it speeds up and vice versa. Thus, there is a direct mathematical relationship between the pressure and the speed. So if one knows the speed at all points within the airflow, one can calculate the pressure, and vice versa. For any airfoil generating lift, there must be a pressure imbalance, i.e., lower average air pressure on the top than on the bottom. Bernoulli's principle states that this pressure difference must be accompanied by a speed difference. Conservation of mass. Starting with the flow pattern observed in both theory and experiments, the increased flow speed over the upper surface can be explained in terms of stream tube pinching and conservation of mass. The streamlines divide the flow around the airfoil into stream tubes, as depicted by the spaces between the streamlines in the diagram to the right. By definition, fluid never crosses a streamline in a steady flow. Assuming that the air is incompressible, the rate of volume flow must be constant within each stream tube, since matter is not created or destroyed. If a stream tube becomes narrower, the flow speed must increase in the narrower region to maintain the constant flow rate. This is an application of the principle of conservation of mass. The picture shows that the upper stream tubes constrict as they flow up and around the airfoil. Conservation of mass says that the flow speed must increase as the stream tube area decreases. Similarly, the lower stream tubes expand and the flow slows down. From Bernoulli's principle, the pressure on the upper surface where the flow is moving faster is lower than the pressure on the lower surface where it is moving slower. The pressure difference thus creates a net aerodynamic force, pointing upward. Limitations of explanations based on Bernoulli's principle. The explanation above does not explain why the stream tubes change size. To see why the air flows the way it does requires more sophisticated analysis. Sometimes a geometrical argument is offered to demonstrate why the stream tubes change size. It is asserted that the top obstructs or constricts the air more than the bottom, hence narrower stream tubes. For conventional wings that are flat on the bottom and curved on top, this makes some intuitive sense. But it does not explain how flat plates, symmetric airfoils, sailboat sails, or conventional airfoils flying upside down can generate lift. And attempts to calculate lift based on the amount of constriction do not predict experimental results. A common explanation using Bernoulli's principle asserts that the air must traverse both the top and bottom in the same amount of time, and that this explains the increased speed on the top side of the wing. But this assertion is false. It is typically the case that the air parcels traveling over the upper surface will reach the trailing edge before those traveling over the bottom. Basic attributes of lift. Lift is a result of pressure differences and depends on angle of attack, airfoil shape, air density, and air speed. Pressure differences. Pressure is the normal force per unit area exerted by the air on itself and on surfaces that it touches. The lift force is transmitted through the pressure, which acts perpendicular to the surface of the airfoil. The air maintains physical contact at all points. Thus, the net force manifests itself as pressure differences. The direction of the net force implies that the average pressure on the upper surface of the airfoil is lower than the average pressure on the underside. These pressure differences arise in conjunction with the curved airflow. Whenever a fluid follows a curved path, there is a pressure gradient perpendicular to the flow direction, with higher pressure on the outside of the curve and lower pressure on the inside. This direct relationship between curved streamlines and pressure differences was derived from Newton's second law by Leonhard Euler in 1754. The left-hand side of this equation represents the pressure difference perpendicular to the fluid flow. On the right-hand side, ρ is the density, v is the velocity, and r is the radius of curvature. This formula shows that higher velocities and tighter curvatures create larger pressure differentials, and that for straight flow the pressure difference is zero. Angle of attack. The angle of attack is the angle between the chord line of an airfoil and the oncoming air. A symmetrical airfoil will generate zero lift at zero angle of attack. But as the angle of attack increases, the air is deflected through a larger angle and the vertical component of the airstream velocity increases, resulting in more lift. For small angles, a symmetrical airfoil will generate a lift force roughly proportional to the angle of attack. As the angle of attack grows larger, the lift reaches a maximum at some angle. Increasing the angle of attack beyond this critical angle of attack causes the upper surface flow to separate from the wing. There is less deflection downward, so the airfoil generates less lift. The airfoil is said to be stalled. Airfoil shape. The lift force depends on the shape of the airfoil, especially the amount of camber. Increasing the camber generally increases lift. Cambered airfoils will generate lift at zero angle of attack. When the chord line is horizontal, the trailing edge has a downward direction, and since the air follows the trailing edge, it is deflected downward. When a cambered airfoil is upside down, the angle of attack can be adjusted so that the lift force is upwards. This explains how a plane can fly upside down. The wings of birds and most subsonic aircraft have spans much larger than their chords. For wings of this general shape, the most important features of the lifting flow can be explained in terms of the two-dimensional flow around an airfoil, which is just the shape of a cross-section of the wing, as illustrated in the drawing at right. Most of the discussion in this article concentrates on two-dimensional airfoil flow. However, the flow around a three-dimensional wing involves significant additional issues, and these are discussed below under lift to three-dimensional wings. For a wing of low aspect ratio, such as a delta wing, two-dimensional airfoil flow is not relevant, and three-dimensional flow effects dominate. Airspeed and density. The flow conditions also affect lift. Lift is proportional to the density of the air and approximately proportional to the square of the flow speed. Lift also depends on the size of the wing, being generally proportional to the wing's area projected in the lift direction. In aerodynamic theory and engineering calculations, it is often convenient to quantify lift in terms of a lift coefficient, defined in a way that makes use of these proportionalities. Lift coefficient. If the lift coefficient for a wing at a specified angle of attack is known, then the lift produced for specific flow conditions can be determined using the following equation, where L is lift force, ρ is air density, v is true airspeed, a is the wing area, and is the lift coefficient at the desired angle of attack, Mach number, and Reynolds number. Pressure integration. When the pressure distribution on the airfoil surface is known, determining the total lift requires adding up the contributions to the pressure force from local elements of the surface, each with its own local value of pressure. The total lift is thus the integral of the pressure, in the direction perpendicular to the far-field flow, over the entire surface of the airfoil or wing, where L is the lift, A is the wing surface area, P is the value of the pressure, N is the normal unit vector pointing into the wing, and K is the vertical unit vector, normal to the free stream direction. The above lift equation neglects the skin friction forces, which typically have a negligible contribution to the lift compared to the pressure forces. By using the streamwise vector I parallel to the free stream in place of K in the integral, we obtain an expression for the pressure drag dP. If we use the spanwise vector J, we obtain the side force Y. The validity of this integration generally requires the airfoil shape to be a closed curve that is piecewise smooth.